Hello guys and welcome to FreeBirds2 and welcome to 75-day Hard Generative AI Learning Challenge, and this is day 11, and in this video I will explain some topics that are related to neural networks and natural language processing, and these topics are vanishing gradient problem and along with the exploding gradient problem. We already learned about the LSTM neural network that is used in the natural language processing for the next word prediction, but we need to know that why we use LSTM over RNN as well, why we use some other algorithms there. Okay, so that's the issue of these two problems. Okay, so we first start explaining that what is this error gradient. Okay, so the error gradient is the direction and the magnitude that has been calculated during the training of a neural network that is used to update the weights of a neural network in the right direction. Okay, whenever you are training a neural network, it gives you some kind of error. And by seeing that error, it is the positive or negative, you try to update your weights in a certain direction. Okay, in that direction, your neural network started to learn. Okay, so that's how it is done. But if we talk about the vanishing gradient problem here, the vanishing gradient problem actually occurs when in our recurrent neural networks, when the gradients, these error gradients of the loss function with respect to the network parameters become extremely small. Okay, so if you just try to multiply a number with 0.1 or 0.001, so that's a very small change in between the parameters. Okay, so this can result in a very slow and stalled learning for layers that are far away from the output layer as well. Okay, so your whole network becomes too slow. Okay, if you see this kind of a graph here, you see this kind of a black line that it started to learn, but at the end it goes down, and the derivatives, these kind of error gradients, goes to 0 or very close to 0 as well, so that your model weights can't get updated. Now, why it happens? So we know that the use of sigmoid function is restricted in training deep neural networks because it can cause the vanishing gradient problem. Okay, this causes the neural network to learn at a slower pace and in some cases not at all. Okay, because sigmoid function can return in only two values, 0 and 1. Okay, so in that way we know that the maximum value that we can find from the sigmoid function is at 0.25. Okay, when we are trying to calculate the partial derivative of the sigmoid function, it reaches the maximum value only at 0.25. If you can try to calculate it, you can just see this calculation as well. Okay, this calculation shows if you put value 0 there, the result is 0. If you put value 1 there, the result is also 0. But if you put value 0.5, then it returns the maximum value of 0.25. Okay, when there are like more layers in the network, the value of the product decreases at a point that it becomes very close to 0, and thus it can cause this vanishing gradient problem as well. Okay, so now that how do you know if you have this vanishing gradient problem in your neural network? Okay, so the very first thing is your neural network learns very slow. Okay, very slow, and then during the training as well, the weights of your neural networks are updated very little as well. Okay, and the model performance is also getting to reduce over the period of time. If you see all these kind of symptoms, then you know that you have the vanishing gradient problem. Okay, now what are the different methods to use to overcome this problem? The simplest solution is to replace the activation function from sigmoid to the ReLU. Okay, because the derivative of the ReLU function is defined as 1 for the input greater than 0 and 0 for the negative inputs as well. Okay, and another technique is you use the proper weights. Okay, while building your neural network, you assign some weights to the neural network. Try to do some experiments with that. Try to reduce those weights or try to increase those weights as per your model performance as well. You can also try to use batch normalization for the each layer input you have in your neural network. Okay. Now let's talk about its mathematical formula here. Okay, So we have a deep neural network, and our gradient of the loss function with respect to the weight is calculated at the each layer in the back propagation. We have this equation that shows that the new weights are equal to the old weights minus this learning rate into the loss. Okay, and this loss can become small or large as well as our problems occur. If it is a vanishing gradient problem, then this loss becomes very small, and if it is a exploding gradient problem, then this loss becomes very large as well. Okay, let's see this Python code here, that we see the sigmoid function and the sigmoid function derivative as well. And when we plot this, we see this. Okay, so this is the actual sigmoid function, and this is the derivative of the sigmoid function. That you see that it's first start to learn very well, but at the end it goes down and the learning becomes stalled or very slow. Okay, so that's why we don't use the sigmoid function in our neural networks. Okay, and if we talk about the vanishing gradient problem here, I built this kind of a code here that can use this neural network with the sigmoid function. We see that how it returns the training and the validation loss at the end. Okay, so when I train this neural network, you will see this. Okay, and that it learns very slow over the whole epochs, and also their training loss and the validation loss is going to stall at the end. Okay, it will not learn much faster. It will not try to generalize as well. Okay, so that's what happen if you use the sigmoid function here. But when we fix this problem by using the ReLU activation function, this whole training becomes so fast. See that in the whole training set, this training happens so fast here. Okay, and also it tries to even generalize more. Okay, it does not get stalled here. It even tries to learn more. The loss are not goes the same way. Okay, it even tries to generalize more and gives you the better output than the above neural network, which gets stalled at the end. Okay, now let's talk about the exploding gradient. Okay, so in the deep neural networks or the recurrent neural networks, error gradients can accumulate during an update and can result in a very large gradients. Okay, these in turn results in a very large update to your neural networks. Okay, that makes your complete neural network become unstable. So at an extreme, the values of the weight can become so large as to overflow and result in the nan value of your weights along with your variables as well. Okay, so this explosion occurs through the exponential growth by repeatedly multiplying the gradients through the network which have the values more than 1. Okay, so if your neural network's weight is updated by the values more than 1, it can explode very soon, because it results in a very high weight updates. Okay, now let's talk about that. How do you know if you have exploding gradients? Okay, the model becomes too unstable. Okay, and that results in a very large update in your weights. The model loss can goes to nan, because you can't keep up with the values that the neural network is giving to you. The model weights quickly become so large. Okay, and the weights also goes to nan as well, because your model is keep on updating with the error gradient values which have more than 1. Okay, so in that way it just completely explode in this way. Okay, now if you see that how to overcome this problem, you can also initialize your weight. Okay, if you have the very large weight to train your neural networks, you can use the less weight as well. You can try some other activation functions. You can try batch normalization. You can try the gradient clipping as well. Okay, just clip the gradient and put a threshold there that above it should not go. Okay. Now you can also use LSTM or even redesign your whole model as well. Okay. Now let's talk about the math. It is completely same as the vanishing gradient. If your loss become very large, your new weight becomes also very large as well. Okay. Now let's talk about its Python implementation. So this is the Python implementation of exploding gradient problem with the solution. So we use the same kind of code here, but this time we use the weight of 100 here, and we also use the from kernel initialization along with the ReLU activation function. So you will see when we use not a good weight for our neural network, how it performs. See, the loss is just exponentially starting to grow in some way. Okay, and the gap between the training and the validation loss is also going to increase. So this is the issue with the exploding gradient problem. And how we solve it? We just try to reduce the weight, and we reduce the weight, the model becomes very fast to train, and also the loss is also going to be the less as well. Okay, so in this way you can interpret these graph. Okay, so the main difference is in the training time only. The training time here is very large, but here it is very, very small over the same number of epochs as well. Okay guys? Okay, so in our tomorrow's video, we'll learn about the transformers, its complete architecture, its complete working as well, so that you should start with the actual large language model fine tuning and learning process. Okay, so just be with it and watch all the videos that I upload in the past 11 days. And if you want to know more about the prompt engineering, machine learning, and data science as well, you can watch my other playlists, and along with the read my blogs on the Medium as well. We meet tomorrow. Thank you guys. Thank you so much.